Mucociliary clearance is an important part of our respiratory defense mechanism. This mucus transport system clears foreign particles and bacteria from the airways. Over the next 20 minutes, we will see, in video recorded by Dr. Stanislav Tatkov, how this important mechanism is affected by temperature and humidity. But let's begin by reviewing where mucus clearance fits into the human respiratory system. Every day we breathe in more than 15,000 liters of air, enough to fill around 1,600 balloons. Even in the most pristine environments, that air is not clean and pure. We inhale thousands of dust, smoke, and virus particles, about 100 bacteria alone every minute. More than 150,000 contaminants each day that, if given free rein, can infect and clog the respiratory system. These foreign particles, viruses and bacteria, are trapped in an extremely sticky mucus layer lining the airways. Mucus carries the trapped material into the larynx in a process known as mucociliary clearance. The physiology of this clearance process isn't completely understood yet. Research continues, but let's take a close look at what we do know. We know that mucus transport to clear foreign particles is driven by motile cilia. Cilia are small tentacle-like structures with a diameter about 1,000 times smaller than a human hair, which beat in an asymmetric rhythm. Cilia protrude from most of the epithelial cells lining the airways, densely carpeting the respiratory tract. This was revealed by scanning electron microscope images. Size is indicated by this scale. The cilia are bathed in a watery fluid. The mucus layer, which traps debris, floats on top of this periciliary fluid, and as the cilia beat synchronously, the mucus layer moves, carrying along trapped particles. Now, the exact mechanism by which the cilia cause the mucus to move remains unclear, and it's the subject of intense research. This particular animation is based on the work of Gaber and Preil. The cilia are shown here in slow motion. In a healthy person, they beat much faster, typically around 15 cycles every second, propelling the mucus about 10 millimeters every minute. Zooming out to a video microscopy recording of live tracheal tissue, you can see the tiny beating cilia as flicker throughout the image, and debris floating on the mucus layer as dark spots moving slowly across the field. This computer model, created by Dr. Maren Talfai from Auckland University's Bioengineering Institute, illustrates the temperature changes in the lung during respiration. Airway temperature is mapped to color from 34 in blue to 37 degrees Celsius in red. Inhaled room air is warmed and humidified in the airways. As you can see in the model, by the time it reaches the trachea, room air has warmed significantly. Heat exchange occurs in the airways, so temperature falls during inspiration and rises during expiration as heat and moisture are recovered. In healthy individuals, this physiological mechanism maintains thermodynamic balance, conditioning the inspired air and preventing mucus from drying out. This is important because, as we shall see shortly, mucociliary clearance fails when the mucus dries out. Recovery of heat and moisture during expiration may be inadequate to prevent dehydration of airway mucus in patients suffering from COPD, bronchiectasis, cystic fibrosis, and asthma. Mucus clearance slows dramatically in these patients. During mechanical ventilation with room air, or bypass of the upper airway by tracheostomy, cool, dry, unconditioned air desiccates the airway mucus. Again, mucociliary clearance breaks down through the dehydration of the mucus. Viscous mucus accumulates in the airways. Coughing, a backup mechanism for clearing mucus, increases to try to clear the buildup. Inspired air, heated to body temperature and fully humidified, restores the physiological equilibrium, increasing mucociliary transport and reducing the need to cough.